Question 7, so we've got some ionization energy data. So first of all, why do the ionization energies, the successive ionization energies increase? Well, the number of protons aren't changing. Every time you remove an electron from the first, second, third, fourth, fifth and sixth ionization energy, the nuclear attraction, the attraction from the protons in the nucleus isn't changing, but the number of electrons are decreasing. So there's the same nuclear attraction for an ever-reducing number of electrons. Therefore, proportionately, the attraction increases, and so it becomes harder and harder and harder, or it requires more and more energy to remove successive electrons. However, the question is asking, 7.1 is asking, which element is calcium? Well, calcium's in group 2, so you removing the first 2 electrons gets increasingly difficult, but removal of the third electron from an energy level underneath, which is full and stable, is going to be very difficult. So there's a jump then between the second and the third, and the jump then I can see is Y. 1150 to 4940 is the large jump. That means that calcium in group 2 with 2 electrons in the outer shell, the third electron is particularly difficult to remove because it's coming from a full stable energy level underneath. Bit trickier this one, vanadium, because you've got to work out that it's 4s23d3. So 4s23d3 has got 5 electrons in its outer 5 outer electrons. 4s2 will be removed first, and then the 3d3 will be removed, and then you're removing from a full 3d2 orbital underneath. So the first 5 electrons are increasingly difficult to remove, but the 6th electron coming from a 3d2, a full suborbital underneath, is going to be difficult to remove. Between the 5th and the 6th, 6280 to 12400 is a large jump. So the answer then is X. Why was it vanadium? So it's just asked me to explain that there's a jump in ionization energy between the removal of the 5th and the 6th electron. So vanadium, which has got 4s23d3, 5 outer electrons, it's likely to be vanadium. An acidified solution of NH4VO3 reacts with zinc. Explain how this reaction shows that vanadium is in at least 2 different oxidation states. The easiest way to note that it's in different oxidation states is when it changed its oxidation state as a transition metal, it changed its colour. So 2 different colours are probably observed, and each colour is due to the vanadium being in a different oxidation state. I think this is one of the hardest questions, or if not the hardest question on the paper. The vanadium has vanadium in 50 centimeters cubed of 0.8 mole decimeter cubed solution. So first of all, I've got a volume and a concentration, so I've got to get that into decimeter cubed, and then I can use concentration as mole divided by volume in decimeter cubed. Centimeter cubed up into a larger unit like decimeter cubed, I divide by 1000, so that's 0.05. So concentration 0.8 equals number of moles divided by 0.05. So my number of moles is 0.8. My concentration multiplied by 0.05, which is 0.04. I'll leave this up as spoilers then for SO2. Slightly more difficult, well, quite a lot more difficult really, because we've got PV equals nRT. We've obviously got PV equals nRT because I've got a volume, but I've got a temperature, I've got a pressure, and I've got a gas constant R. So I've got PV equals nRT, so it's relying on me knowing the second equation. And what's also tricky is that these aren't in the right units either. 506 centimeter cubed for PV equals nRT. The volume's got to be in meters cubed. So centimeters cubed up into decimeter cubed, you divide by 1000. 506 divided by 1000 is 0.506. And then to get up into decimeter cubed, up into a larger unit still, to get up into meter cubed, it's divided by 1000 again. So it's 0.0000506 meters cubed. If that weren't tricky enough, then you've got degrees Celsius, and that needs to go into Kelvin. So you've got to add on, therefore, to get into Kelvin, then you've got to take your temperature, 220, and add on 273 to equal 298. So now we've got the temperature in Kelvin. Now we've got 98 kilopascals, and that's not correct either. You've got to get that into pascals, and so a large unit down to a smaller unit you multiply by 1,000, so that's 98 multiplied by 1,000 is 98,000 pascals. PV equals nRT, we can start putting these in now. P is 98,000, volume is 0.000506, equals N, the number of moles, multiplied by 8.31, which we're given is the gas constant, multiplied by the temperature in Kelvin 293, and I've got that there. I'd multiply these two out first, make it simpler. 49.588 equals N, the number of moles, and I'd multiply these two out, 2434.38, so N is 49.588 divided by 2434.83, 0.02. So this next stage is difficult now, even more difficult, because we've got to work out, we're working out that 0.04 moles of this reacts with 0.02 moles of this. So I've got 2 moles of the vanadium compound reacting with 1 mole of the sulfur dioxide gas. It's reacting in the ratio 2 to 1. So 2 moles of the vanadium compound react with 1 mole of SO2. So what's happened to SO2? Well, SO2 reacts to make sulfate ions, SO42-, and you can produce a half equation from that. How can I get that making that? Well, I've always got water and H plus that I can always add into a half equation, and electrons, of course, always needed in a half equation. Water and H plus to add in. So I'm going to need more oxygens on the left hand side because I've only got 2 O's and I've got 4 O's there. H2O, I'm going to need 2 H2O to make the O's balance, 4 on the left and 4 on the right. And now I've got 4 H's, I can make 4 H plus. So to balance a half equation involving H's and O's, I can always add water and H pluses. And now if I look on the right hand side, I've got 4 pluses, 2 minuses, I've got 2 electrons. Okay, so 2 moles, so I've got to get the 2 electrons. Where do they come from? They come from the other chemical that reacts, the NH4VO3, that's where the electrons come from. So 2 moles of NH4VO3, rather, are not going to make 2 electrons, they're going to absorb 2 electrons, remove 2 electrons, so 1 mole of NHVO3 will remove 1 mole of these electrons, so the oxidation state is going to go down by -1. If it accepts an electron, its oxidation state is going to go down by -1. NH4VO3, its oxidation states of N are in -3, H is +1 and O is -2. Because N is in group 5, accepts 3 electrons, H is in group 1, loses 1 electron, O is in group 6, gains 2 electrons. So now I can do some simple sums. -3, add 4 times 1. V, we don't know the oxidation state. O is 3 minus 2's, and that's all got to equal 0 because there's no charge on this. And so my oxidation state of my vanadium must be +5 to make all of those numbers equal 0. If it's going down by -1, because it's accepting an electron, so it's accepting a minus and going down by -1, its new oxidation state must be 4.